All right, well, I'm not going to cut off the questions for Jenna. If some arise, and they certainly will, please put them in the chat box. I want to start off by thanking Adam first for the invitation to come and talk about Cyclops. I know many names in Odyssey are a little obscured. Cyclops is an acronym for cyclic descent for logistic, Poisson, and survival. Along with being a great acronym, it's also one of the workhorse packages of the Odyssey tool stack, although most of us users are not familiar with it. To give you some background, Cyclops forms, or at least performs, almost all of the large-scale regression that people normally start with in patient-level prediction for the self-controlled case series and the cohort study. I have two aims this morning. The first is to give everyone a flavor of what high-performance software design looks like at scale. And my second aim is to make sure that we make it to our keynote talk on time. So hopefully I'll at least succeed in the second one. Cyclops is based for very large-scale models, and large-scale models are generally regularized regression. And the idea behind regularized regression is that one allows the model to decide which aspects of the data, in particularly the covariates, help describe the outcome that we're interested in without overfitting. Regularized regression has a very long history. People are much less familiar with the 1970s work in ridge regression and perhaps more familiar with the L1 or lasso regression that became popularized right before the turn of the last century. These are all forms of regularization in slightly different spaces, and Cyclops is a high-performance approach to doing this type of regularization for many different types of penalties. There are some big advantages to large-scale regularization, and that is that while the estimates that you get in terms of the coefficients might be modestly biased, that bias tends to go to zero. They perform much better in terms of the mean squared error of the model, and some regularizers like L1 regularization lead to much better prediction. The way that Cyclops handles very large scale data for many different regularizers is to use a cyclic coordinate descent approach, which is something that we won't necessarily go into in our discussion here, beyond saying that you have a large parameter space, you take a large number of small steps, and you vary the direction in the parameter space that you're working in. This reduction of trying to directly go to the optimal point in your parameter space versus a lot of very small steps helps to simplify the calculations that you need to do, and also allows one to think about a very general way of building a package that allows you to do many different types of regressions very efficiently. And Cyclops itself, in addition to doing sort of standard linear, logistic, and Poisson regression, is also able to accomplish many of the conditioned models which other packages fail to approach, but are very important for observational data. You know, a self-controlled case series would use a conditional logistic regression. A self-controlled case series uses a conditional Poisson model. All survival models are conditional as well. The challenge, however, at scale is conditioning for fitting a case-controlled, self-controlled, or Cox model leads to a very expensive likelihood calculation of the data, because not only does that calculation involve the contribution of each of my data points, how they're pointing me towards the mode, but one needs to adjust for the fact that the conditioning fact that a number of events have already happened. One way to get around this very expensive likelihood calculation is to use cyclic coordinate descent. Cyclic coordinate descent has some real advantages because it allows you to take one to take advantage of the sparsity of the covariates themselves. So many of the covariates that you'll find in a predictive model are 0-1 indicators for the presence or absence of some drug use or some condition during some time period. So most of those entries are 0. The remaining very small entries are 1 or a number. And it scales well for very tall outcomes, so the number of patients that we have. Cyclops itself has been in development now for over a decade. There are a couple of early manuscripts in the work and much more coming. So one might ask, wow, you're fitting large-scale regressions. Aren't there lots of packages out there that do that? And why does the Hades tool stack really rely on Cyclops, and why should I get involved? Well, there are a number of packages out there. Some of the most popular are one called Big LM, and this has really been engineered for big N, so large numbers of patients, but very small numbers of predictors. And when you have this tall, narrow model, you can take advantage of very standard matrix factorizations that have been around since the 1970s to lead to sort of, low rank decompositions and the work. But because they're doing matrix multiplications, they don't scale as P gets much, much, much larger. Out in the machine learning world, and its intersection with R, there's a package called GLMNet, originally from Jerry Friedman, in the early turn of the century. Its big advantage is it exploits the sparsity in the number of predictors, but it's been engineered for a large number of predictors, but a very small number of outcomes. And that's not the case we find in our large observational studies. Both N is big and P is big. So if we're working in both dimensions, we really need to exploit some high performance statistical computing. Some of the ideas that Cyclops likes to build on are massive parallelization. We have lots of operations that we could do at the same time, and overcoming the real limitation of large problems, which is the memory bandwidth restriction that you have in most computers. We're no longer restricted by the number of floating point operations you can do. We're mostly restricted by how efficiently we can move information from a database in memory, from memory down through its caches onto the CPU itself. We currently use cyclic coordinate descent, but there's a lot of advances in other parallelization approaches like MM algorithms, which are coming for Cyclops. Let me start off by talking a bit about the Cyclops workflow. It's a little unusual compared to its major competitors. Our workflow at present really consists of 2 separate steps. The first step is a data wrangling. So this is loading your information either from file or from database into memory. And then the second step is actually doing the model fitting on the in-memory object. And the advantage of breaking this work up into 2 different functions, create Cyclops data, fit Cyclops model, is it exploits data reuse, and it allows for very simple multiple wrangling implementations. You can come direct from database, you can come from file. The data reuse comes in when you start thinking about cross-validation or fitting multiple models. I don't want to have to do that load again. I just want to act on the data object itself. But an easy place for individuals to get involved in Cyclops development would be providing a one-step wrapper, which is very standard in R. For those of you that fit logistic models, there's a GLM function that does both the wrangling and the model fit. And that should make Cyclops, as an easier on-ramp for other users in R if we had that one-step wrapper. So Cyclops is currently engineered for a large number of different model types. Very recently, we've added an additional type of survival model called the fine-grained proportional hazards model, which allows for competing risks. And the model specification that you specify really tells you what are the required data fields that you're going to need in the data wrangling step, and throws everything out for computational efficiency. The way that there are 3 ways to do this wrangling. The first is kind of the standard R formula approach that many R users are familiar with, and then a specification of the model type that you're going to use. What's a little different about Cyclops is in terms of the standard model, we also have a right side only model formulation. So here's, my model, and it just involves treatment. And this allows us to specify ahead of time that our treatment covariate is not dense. You don't need to read every single value, but it's of an indicator format, meaning most values are 0 and a couple of them are 1, and all I need to store are the numbers that are 1. So this is sort of an example of how that leads to a reduced amount of memory usage. My dense treatment indicator is a whole bunch of 0s and 1s, right? But if I want to access it, I have to access all n values every time I take a step in cyclic coordinate descent. Whereas what I can do here is just keep track of the entries that are non-zero, and in case the values that they have here. And so my data access is no longer the total number of outcomes, but it's really only the number of non-zero values. And if it's an indicator, it's directly the non-zero values because I know the value I'm going to be using is 1. If it's not 1, it's just sparse, and I have to read that value as well. There's a number of summary functions that will tell you how this information has been wrangled in memory for use. Another way to load data in is directly from SQL or a SQL-based object. And this is used very heavily in our Odyssey tool stack, particularly the self-controlled case series and cohort method. I rarely use it interactively, but programmatically it's very helpful. Naturally, you can turn off regularization and you can just use Cyclops to do standard maximum likelihood estimation. One would specify it by, I'm fitting the model and my regularization prior is just that there's no regularization, and you get the standard output that you would get if you were using GLM or any other object. However, you can do it a whole lot faster. So let's start by simulating a very small conditional logistic regression. So this is a case control series involving 10,000 people that have been stratified into 200 different match sets. And I'm going to keep track of what my true simulation effect size estimates are. And I'm going to fit it in 2 ways. First, I'm going to fit it using Cyclops. And then I'm also, for Cyclops equal true, and then I'm going to fit it using the best leading competitor for conditional logistic regression, which is a package called CLogit. These data are very sparse. Almost all of the covariates are, 99% of the covariates are 0. If you fit it with the best competitor, CLogit, it takes, almost 3 minutes to fit. In Cyclops, it's 0.3 of a second. So, paying attention to how your calculations are done, doing appropriate data wrangling, and using that sparsity is very important. But there's more going on over the head, under the hood, than just than just wrangling the data appropriately. What really is going under the head to lead to this very high performance for many different types of data, dense data, sparse data, indicator data, lots of different models? Well, the key trick here is using C++ templates. And we'll talk a little bit about template or meta programming in the next couple of slides to give individuals sort of a flavor of what high performance statistical computing looks like. But the key idea is these templates allow us to write code once very expressively and convince the compiler to then compile multiple versions of the code that are really specialized for each of the cases that we might want to be using. And so under the hood of Cyclops is a fair amount of C++ code. Here's some boilerplate C++ that I understand that most of you aren't familiar with, but this loop right here is the key engine for Cyclops. And basically it just says, give me an iterator of whatever type you pass me. The compiler will figure out the best way to index through it. And then let's index through each element of this loop. For each element, if it's dense, it's every single one. If it's sparse, it's just the non-zero ones. Tell me what your value is. And then let's let the compiler delegate to each of our different models sort of the calculation that you need to do if it's a logistic regression or it's a Poisson regression. And what's nice is the compiler will do this delegation for each of our different models and only use the information or the data that it needs. Also, these types of functions will then be inlined, meaning there's no function call in this really hot loop. And it's function calls or jumps in memory as you're computing that tend to slow down a lot of the work that we're doing. So how do you get into or start thinking about the advantages of meta programming for performance? Well, the link that we're using from R to C++ is a wrapper package called RCCP. RCCP allows you to directly access some vector that's been sent from R. So here's a left-hand side and a right-hand side from R. I'm going to add those two values together, and I'm going to return what the result is. But C++ alone doesn't give you this compile time optimization. So if you really want performance, I would recommend whatever you're doing, you consider using a templated linear algebra library. And two of the most popular out there are Eigen and Armadillo. These templates are a form of use expression templates, which are a form of metaprogramming. So what's metaprogramming? Metaprogramming is writing a program that when that program gets compiled or executed, it isn't just compiled into machine code. It actually writes new code that the compiler then looks at again to generate a diversity of highly optimized work. So let's get a sense of really what's going on if you're not paying attention to your performance. So here's a very standard expression that you might do in R. I have a vector, it's length of 1,000,000, and I want to add it to itself 4 times. We might think this is a really fast operation, but it turns out if it's not done well, it can be very inefficient. Let's look at what's actually going on under the hood. And to do that, we'll use a little C++. So I've written a function that we'll look at. It's, we're going to execute an algebraic expression, and it takes our 4 input vectors and it returns a result. Okay. So it's going to take input vector A, it's going to add it to B, add it to C, add it to D. You'll notice that this is a very expressive statement. It's kind of easy to read. A plus B plus C. But those of you that know C++ will say, but C++ doesn't know how to add vectors together. One of the nice things is we can use some syntactic sugar. Syntactic sugar is writing small bits of code that hide very complicated operations. So what does R do when I want to add vector A to vector B? Well, it calls a function called add, which adds my right-hand side and my left-hand side. So every time we add something to this, we're going to create a new result. And then in that new result, we're going to add the right-hand side to the left-hand side and return that result. So this is what's going on in R. So if we were to compile the C++ or the R code for A plus B plus C, what it really generates is make a temporary vector. So I need to allocate 1,000,000 values in memory. I need to add A and B together. Now make a new temporary vector and add the first temporary to C. Make another temporary vector, do it again, and finally return that last temporary vector. And generally, if you don't do anything smart, the compiler is smart enough to optimize away this last copy. You don't believe me that all these copies actually happen if you're not paying attention to your code? Well, we can write a very small wrapper class over the numeric vector that we get from R. That all it does is when I create a new vector, it keeps a count of how many times did I make new vectors. And we'll run the code. So let's micro benchmark the algebraic expression versus the simple loop that I just wrote using this new code. And we, in milliseconds, the only statistic that's really important here is they both took 11.5 milliseconds on median, right? So, C++ is great. One of its dictums is you don't pay for what you don't use. So I've written this wrapper class that's keeping track of extra information, and I'm not paying for it. But what it does provide is when we're running that, it does tell us how many new vectors did we have to create where temporaries really made. And yeah, if you run the C++ code or R, you have to make and destroy each time you're doing it 6 million length vectors. That's really going to slow down our performance. What we'd really like is code that does the following. It takes a place in memory where it's going to store the result. It takes the 4 input vectors, and it just runs a single loop, right? And where in that single loop for each element, it does its component-wise add. So this is called loop fusion. So ideally, we'd like to program in something very expressive, A plus B plus C, and have the compiler transform it into this loop fused operation. So let's run the loop fused operation just to demonstrate to ourselves that it really is a lot more efficient, right? The R code takes 11 seconds. The loop fuse code takes 2 seconds, right? So it really is much more efficient. How do you get from expressive code that we're going to write in something like Cyclops for many different models all the way down to that fused operation? Well, the trick there is using expression templates or template meta programming. So I can provide a small little header file which defines some expression meta programming, where what I do is I just write, I want my result equal to A plus B plus C. And the compiler will know not to generate any of those temporary intermediates and will immediately translate this tree of operations, right? A plus B goes to an intermediate. That intermediate is added to C. That resulting intermediate is added to D, right? It's a tree of operations get transformed into a single assignment, right? Don't, traverse this tree each time we're making the assignment. Don't do it for all of the intermediates, right? So we end up getting something which is called a lazy evaluation, such that the expression, not the value A plus B plus C of I, only evaluates for the I entry, and then we just have that simple loop over the n values that we need to do. Or if it's sparse, not over the whole matrix, but only over the non-zero entries. Expressions are trees. I'm not going to go into how you write in too much detail, kind of expression templates. Most of these days, we end up really using libraries that do that. But we can have the compiler transform A plus B into this tree of operations, where when we just say evaluate, it does it element-wise and returns it for value I. So we'll do a benchmark. We'll do a benchmark between our hand-coded transformation, so this is the ideal code that we want, versus using the expression template with that really expressive, A plus B plus C. And yeah, they compile down to exactly the same code. So with expression templates, it's relatively forward to extend your template class to handle many different operations on large vectors and matrices. Dense or sparse are indicators, where in the C++ code, you just have to write very simple commands like, take A, multiply it by B, divide by C, right? Lots of scalar operations. and that gets compiled down to the code that we really want to execute. So for Cyclops, we have a number of these element-wise vector operations that we want to be executing for each different model, and we can write them as simple algebraic expressions. If I want the derivative of the likelihood with respect to one of the regression coefficients, because I'm going to search through this space, right? Then I need to take a dot product of my outcome versus times the covariate, and then subtract off some variance term on there. And these expressions differ from model to model, but they don't differ very much. So we can extend to a new model just by writing, one new line of code for what's the new derivative, and then allow the underlying metaprogram to do the appropriate transformations of these simple operations into code that develops no intermediates and reuses as much of those calculations as possible, right? So, intermediate values, you might see that there's some weight function here that gets used both in the first and the second derivative. So we'd like to fuse computation of the first and second derivative so that we only have to compute W once and really never even have to store it to memory. It can just get used immediately. And that's exactly what we do in Cyclops, right? A new model is just a simple algebraic expression with a simple algebraic line where the underlying expression templates take care of removing all of the temporaries and doing the operation as efficiently as possible. This is just kind of a benchmark without, with using some expression templates, but not all. Ideally, we're going to set up, some expression template for the gradient and the Hessian, but I don't want to evaluate them yet because they both reuse some values here. I only want to evaluate them once when I go and I add them together, and that decreases the number of copies that we actually need. In order to keep us on time, I'm going to say there's lots of fun stuff that one can do with very expressive meta programming. It's not restricted to C++. You'll find it as one of the key tenets of many modern languages like Julia, but C++ itself has had a real renaissance in the last decade because of this type of work. So as a quick summary, for using expression templates, sort of fusing your transformations and reductions, they allow you to avoid intermediates so that extra values that you don't need to be saved to memory and read back in. What does that do? That reduces your memory bandwidth, right? The amount of information you need to be moving back and forth, which allows us to generate code which executes for very large models. The compiler itself can optimize the order in which it does operations so that they're done most efficiently. And it's a straightforward way to generalize your expressions for offloading onto advancing computing technology like vector operations on the CPU, so something called SIMD, vectorization across multi-core work, or many core work on graphics processing units. You have to write once, and then you allow the compiler to then compile for all of these different devices as optimized as possible. So developers are certainly needed. Directions that we're going are extending into sort of time-varying survival models. And so we still need to think about some work in unique data representations that are memory and compute efficient for these types of models. There's active work in massive parallelization. One place that would be useful would be constructing a compute environment that has both good access to graphics processing units, the Hades tool stack, and some real data sources, because we currently have a limitation that the data sources are in one environment and good computing is somewhere else. And there's lots of emerging inference procedures. Bayesian approaches are coming in, iterative hard thresholding for different types of regularization. So there's lots of work to be done for people who are interested in high performance computing. And with that, hopefully I've achieved two goals, given some flavor of what goes into very high performance computing, and hopefully have interested some individuals in exploring this further. And I've certainly kept us on time for the keynote. So thank you.